Hi students, and this is the video lecture on shift registers. You have already done shift registers in the lab classes and it is very simple. So if you have time, just go through this once. That will be enough to understand the shift registers. First, I would like to tell you about the shifting operation and the effect of the shifting operation. Suppose you have a string of bits which is in binary numbers system, or string of digits in a decimal number system. So shifting operation, if your bits are shifted in the left direction, it leads to multiplication. If the bits are shifted in the right direction, it leads to division. This is how division and multiplication is done in computers when it is in the binary format. Let us see one example. 6 into 2 is equal to 12. 6 in binary is 0110. 2 in binary is 0010. So when you multiply it, this is the first partial product, 0 into this, and then 1 into this. You have all the other partial products as 0, and when you add, you get 01100, which is nothing but 12. So 6 into 2 is equal to 12, and in binary also you get 12. Okay, simply you can get the answer by shifting your 6 in the left, the bits of 6 in left by 1 bit. So if this one comes here, if this one comes here, it becomes 1100, which is nothing but 12. So shifting the bits in the left direction will lead to multiplication by 2. Similarly, shifting in the right direction will lead to division of the value by 2. So the same thing is applicable to decimal number system also. So take a decimal number system. Usually we will do like this. For multiplying by, the base is 10, so for multiplying by 10 we will shift it to the right by adding 1 0 to the rightmost position. We will shift it to the left. Okay, we will add 1 0 in the rightmost position. Similarly, dividing by 2, we shift it to the right direction. So the same thing is applicable to a binary number system. So in base 2 number system or in binary number system, the binary point, okay, if the bits are moved, it is in the left means multiplication, right means division. If the binary point is moved, right means multiplication, left means division. Okay, so now here is another example. 1110 into 2. Okay, 1110 is 14. 14 into 2 will lead to 28. Okay, 28. This is 4. This is 8 plus 16. Okay, so this is the the representation for 28. Similarly, when you shift 28 by one position in the right direction, you will be getting 1110, which is nothing but 14. Okay, so for dividing by 2, you have to move it in the right direction, and for multiplying it by 2, you have to move it in the left direction or shift it in the left direction. Okay, now this shifting operation actually leads to multiplication and division, but we have a family of circuits which is called as shift registers. It's a family in the sequential logic circuit, and it can be used for data storage and transfer of binary data in some format, in parallel format or in the serial format. These two are the basic types of data transfer: parallel transfer or serial transfer. So shift registers can be used as storage elements and also for shifting the data. Okay, this kind of circuits will load the data present in its input pins and then moves or shifts to the output once in every clock cycle, and hence it is called as shift register. So there will be a data movement only once in the clock cycle with respect to the clock cycle, and it takes the data also with respect to the clock cycle. Okay, so now this is not used for the arithmetic multiplication and division. Okay, even though the shifting leads to multiplication and division, it can also be, this shift registers can also be used for storing and transfer of data. The basic components in a shift register is D flip-flops. Okay, because D flip-flops are data flip-flops or storage flip-flops, so it is the simplest flip-flop. It can be used for data storage. So usually we will use D flip-flops, and the number of flip-flops required will be the number of bits you want to store, and then they will be connected in a serial manner, series daisy chain arrangement. That is, output of one flip-flop will act as the input to the other flip-flop, and so on. So data is fed one after the other in the right or left direction. You can have either right input or left input, or all together at the same time in a parallel configuration. All the bits can come in parallel also. So all the flip-flops are triggered by a common clock. Okay, it is a synchronous sequential circuit. So all the flip-flops will have a common clock. And there are 4 types of shift registers. Okay, as I told you, there are 2 types of data transfer patterns. One is parallel, another one is serial. So the input can be either parallel or serial, and the output can be taken either in parallel or in serial. Okay, so these 2 combinations in both input and output will lead to 4 different types of shift registers. That is serial in, parallel out, serial in, serial out, parallel in, serial out, parallel in, parallel out. Okay, that means serial in, serial parallel out means your input comes in serial but the output goes in parallel, and then serial in, serial out means your input comes in serial and output also goes in serial. And parallel in, serial out, you take all the data bits parallelly, but you output it one after the other. Parallel and parallel out, in one clock cycle you take all the input bits, and in the next clock cycle you give all the outputs, all the bits out. Okay, so these are the types of flip-flops, and serial is slow, parallel is fast. Okay, so depending on this, your time taken for the data transfer will change depending on the configuration and type of shift register. The time taken will change. Okay, so the applications of shift registers are, registers are for storage. So here for storage you can use parallel in, parallel out for data storage, and then serial data transfer. For serial in, serial out, you can use it for serial data transfer, and then for serial in, parallel out, and parallel in, parallel in, serial out can be used for communication between systems which use these 2 types of data transfer. Okay, for example, in computers the data is processed in parallel, but its peripherals will take it in the serial. You have serial ports also. So for the serial ports will take data and it will give data in the serial fashion. So when input goes from a serial port, you should have a serial in, parallel out shift register. Similarly, from the computer, when you give it to a serial port, you should have a parallel in, serial out shift register. Okay, so this is, for example, keyboard encoder also. One you need this serial in, parallel out data transfer. Okay, so the data movement will be like this. So this is the 4-bit register. So the 4-bit register, you need only 4 flip-flops. Okay, now the using the basic 4 flip-flops, you can form it in any of the 4 combinations or configurations which is given above. So serial, the data can come in serially, and for every clock cycle it can move from one flip-flop to the other. So from here to here, here to here, here to here, and here to this in the 4th clock cycle. So this is called a serial in, serial out data transfer. Okay, it will take that bit which comes here, it will take 4 cycles to come out here. So after the 4th clock pulse, you will get the data, first bit of the data. If you have 4 more bits, it will take 4 more cycles to come out. Okay, and then you may have a parallel data in. So parallel data input can be given to the flip-flops in parallel. So in one clock cycle you can take all the data bit. Similarly, you can take all the data out from the Q outputs of the flip-flop. So this is also possible. Sometimes you may take the data parallelly in and transfer it one after the other. Okay, so for loading you will take one clock cycle, and from the next clock cycle it can come out one after the other. So it will come, in the second clock cycle you can get this bit, in the third clock cycle you can get this bit because this would have been transferred here. In the fourth you can get this, in the fifth you can get this. So a 4-bit data can be obtained in 4 clock cycles. Otherwise this is called as parallel and serial out. And you can have serial in and parallel out also possible. So if I have 4 bits here, all the 4 bits can be transferred to all the 4 flip-flops in 4 clock cycles, and after that I can take it parallelly out. Okay, I need not wait for 4 more cycles to take all the bits out. So that is called a serial in and parallel out mode. So these are the possible types of data transfer with a 4-bit shift register which is formed with 4 flip-flops. Okay, now 4-bit serial in parallel out. Okay, I have already explained this. So you have a serial data in, you will have a common clock, okay, and then you will have a clear input. So if you want to clear it, you can clear it first. You can clear it. Usually you have to do that. So reset it so that all the flip-flops will have 0 as its output. And now this serial in parallel out. Okay, so this data comes in. Suppose I have 1 0 0 1. So the first clock cycle 1 will come here. In the second clock cycle this 1 will go here and the new 0 will come here, and in the third clock cycle the third bit 0 will come here, this 0 will go here, this 1 will go here, and for the fourth clock cycle a 1 will come here, the 0 here will come here, the 0 here will come here, the 1 which is here will come here. So after 4 clock cycles I have 1 0 0 1 here, and now in the 5th clock cycle in 1 clock I can take all the 4 bits out. This is called as serial in parallel out mode. Okay, so the operation is explained here. Okay, so here we have the data as 1 0 0 0. Okay, not 1 0 0 1, it is 1 0 0 0. So this 1 will go shifted towards this in 4 clock cycles, and in the 5th clock cycle we can take this out. Okay, the next step of configuration is serial in serial out. So same serial in parallel out. Serial in serial out using the same type of 4 flip-flops, but here you don't have parallel output lines coming. You have to take it only at the last flip-flop. So the data which comes here, it will take 4 cycles to shift up to this, and then it will take 3 more cycles or 4 more cycles to get shifted out of queue. So it will take a long time. Serial in serial out will take a long time for data transfer. And then parallel in serial out, the data is loaded into the register in a parallel format where all the bits enter simultaneously to the parallel inputs to all the 4 flip-flops A, B, C, D. The data is read out sequentially in the shifted mode. Okay, so now the data will come out from PD. The MSB will come out first, and then at that time the last bit 1 would have been shifted to the last, and it will be shifted, and so on. Okay, this is the configuration. We have 4 bits coming in directly, and then the output will come one after the other. And the next configuration is parallel in parallel out. You have 4. You will have a common clock, but the inputs are different. T will be connected to 4 input lines, and Q will be taken out directly. There is no interconnection between the flip-flops. So this is actually register. You will do array of D flip-flops which forms a register. So this is actually used for data storage. This is fast. In 1 clock cycle you can load, and in the next clock cycle you can take the output. So this is the storage RAM. This is actually a RAM. An array of such flip-flops. Okay, if I have a few more rows of D flip-flops, it will form a RAM. Okay, bidirectional shift register, it can move in either direction, in the shift right or shift left, or in parallel and in serial mode and so on. This is made possible using 4:1 muxes as the control signals and so on. Okay, so you will have mode operations depending on the select bits of your mux. 0, 0 for hold no change, 0, 1 for shift left and so on. These signals will act as a control signal for the shift register. Okay, now this ring counter is a counter because it goes through a definite number of sequences. What is it's formed of a shift register because it uses only D flip-flops. Okay, so take a serial in, serial out shift register connected back to back. Okay, connected back to back means the output of the last flip-flop is connected as the input to the first flip-flop. Okay, so it is a serial in, ring counter is a serial in, serial out shift register connected back to back. This the output of the last flip-flop is connected as the input to the first flip-flop. Okay, and this forms a closed loop. And whatever you given can circulate inside the flip-flops, inside the 4 flip-flops. Okay, the looping of the output back to the input is called as feedback, and you can convert a standard shift register into a ring counter now. Okay, so see the configuration. You have the clear. So there is a preset signal. So first time you set this to 1, initially everything will be 0, and for the first clock cycle this will be 1. Okay, after that this is cut and this one comes here. Okay, so now 1 0 0 0, and in the next clock cycle this 1 will get shifted here, the 0 will come in here. So 0 1 0 0, the next clock cycle 0 0 1 0, the next clock cycle 0 0 0 1. So this is how the sequence will go. So as we know the sequence, it is called as a counter. Okay, so it is a rotation movement of 1. This 1 is rotated over this. This 1 is rotated over this. So first QA is 1, then QA becomes 0 because it is connected with this. Okay, this is already 0. Okay, so initially everything is 0, and then 1 is, this 1 will shift through all the flip-flops. So this is called as a ring counter. Okay, so these are the states of the ring counter: 1 0 0 0. So out of it's a 4-bit register, so you have 16 different combinations, but only 4 combinations you will get. Okay, so it is called as modulo 4 ring counter. So for a modulo n ring counter, you need n number of flip-flops. So ring counter can be used for various patterns, for getting various patterns. Okay, and there is one more type of shift register which is called as a counter Johnson ring counter. Okay, this is called as twisted ring counter because the complemented output of the last flip-flop is connected to the first input of the first flip-flop. So the inverted output Q bar of the last flip-flop is now connected back to the input of the first flip-flop. You will have two n different states. So Q bar, okay, Q bar of the last flip-flop is connected over here. So initially everything is reset, so this will be 1. Here this will be 0 and this will be 1. So this 1 will come here and this 1 will be shifted here. Again this will be 1. So again that you will get one more 1. You will get one more 1. You will get one more 1 until this becomes 1. So when this becomes 1, this will become 0. And now then zeros will be introduced here. Okay. So now your pattern will be like this. Initially everything is 0. First level becomes 1, and the 1 gets shifted, and then everything will become 1. So when the last flip-flop is 1, Q dash of that flip-flop will be 0. Now 0 will come into this. So now 0 will get introduced into the string. Okay, so this is called as a Johnson counter. Okay, so this can be used as a frequency divider, because if you take any frequency divided by different values. Okay, so you can take any of the output of the flip-flops, you will get some original frequency by the divided frequency. Okay, so you can create different patterns and so on. So okay, that's all about shift register. It's a very small and simple topic. Only in practical it is difficult to implement it, because you may get so many, what is it, what the flip-flop should work properly and so on. Okay, all the best for your exam. Prepare well and write well. All the best. Bye.